So let's get into our last bit, which is polarity and water. So water is polar, right? Meaning that the molecules, each individual molecule water is going to stick to other water molecules because of these hydrogen bonds. Again, we're not creating some massive new molecule. Each molecule is still water, but they have a weak attraction, and that weak attraction actually does add up. But since these bonds are weak, you can constantly break them and remake these hydrogen bonds over and over and over again. So let's draw that out. If we see that, we see each of these space-filling models as a water molecule, and we see those hydrogen bonds drawn out in the dotted lines between them. But you could break that bond and remake it over and over and over again. That brings us into water. Why are we even talking about water? But water has some really cool, awesome properties that allow life to even happen, right? And we can break them to 4 major properties that contribute to water being used for life. One of those is cohesion. So cohesion and adhesion is basically the fact that water molecules can bind together and stick together through the hydrogen bonding. So you think about these really tall trees. Being from California, there's these massive sequoia trees, right? These huge, massive old trees that are really, really tall. And if you know anything about trees, or you know they have a root system, and the root system is used to bring up water. But that water is down on the ground, and those roots are underground. So how do we get water all the way to the top of the tree? We're using the properties of cohesion to get water up through the top. So because of that, water is going to evaporate from the leaves throughout the tree, including at the top. As that water evaporates, it's actually going to pull water molecules up behind it. So it's like a constant stream of water molecules going from the roots up through the trunk, up through the branches to the leaves. And that water column basically never stops. As water leaves the plant, it's pulling water along with it. And so it's constantly moving through the plant. So cohesion is a really, really important property in that, we're looking at plants absolutely rely on this property just to move water through their systems. Right, so we see that here, right? Here's this huge tree, super, super tall, right? And water is coming from the bottom, but how the heck do we get it all the way to the treetop? Right? How do we move water 300 feet? And again, as the water evaporates through the leaves, and it's gonna pull with that hydrogen bond being formed between the two, it's gonna pull on the water molecule that's next to it. And that water molecule is gonna pull on another, and then another, and another. And so it's almost like a string of beads, right? If you pull a necklace from one bead, you're gonna pull the string that has the rest of the beads along with it. Another interesting property and special property of water is its high heat capacity. This means that it's really hard to change the temperature of water. It takes a lot of energy. Right? Think about when you make dinner, right? I'm a huge foodie, as you guys will learn. I love food, and one of the things I really love is pasta. And what do you have to do with pasta? You have to boil it. How long does it take to boil a pot of water, though? Right? Is it instantaneous? No. Is it even quick? No. It seemingly takes forever, right? It takes a long time, and you have to turn the heat up, right? You're turning your burner up to a high heat, and you have to sit and wait. There's a reason why it takes that water pot so long to boil when you're trying to make something like pasta. It's because you have to pump a lot of energy into that water in order to raise the temperature up to a boiling point. This is what, while it might be annoying when you're trying to make dinner, it's actually really helpful for us. So it's going to allow large bodies of water, like the oceans, to absorb huge amounts of heat without changing temperature very easily. It's also kind of sort of one of the things we use to help keep us cool too. So when we sweat, right, it's hot out and we're sweating. As our sweat evaporates, it's going to actually be pulling heat energy. It's going to take energy, like heat energy, from our body as that evaporates, and that's what gives us a cooling effect as well. right? And so we see that, right? Heat is from the sun is going to disrupt, is going to break some of those hydrogen bonds, right? But as fast as those bonds are broken, new ones are going to form just as quickly. So we break this bond, a new one forms almost instantaneous. So if you think about it, like how hot the sand on a beach is versus how hot the water is, it's a huge difference, right? That sand, you have to like wear shoes on, right? Or you have to do a really quick run. You're doing hut, 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 right? All the way across the sand. And then you get to the water and you dip your feet in and it's like instant relief. It's all of a sudden nice and cool. Well, what's the reason? There are not hydrogen bonds like there are between the water molecules in between the molecules of sand, right? We don't see that. And so the sand heats up super fast and gets really hot and stays hot, but the water stays pretty much the same. Another awesome property of water is that it is less dense when it's a solid compared to a liquid. Right? Think about a glass of ice water. Right? Maybe go make yourself some ice water now. Hydrate. Right? It's good for you. What happens to the ice? Does it stay at the bottom of your glass? No, right? It floats to the top. So ice being less dense than liquid water is actually pretty weird. The fact that ice floats is actually really strange. Most solids are more dense than their liquid state. So this is rare. But it's absolutely necessary for life. You know, if you think about a lake and how it freezes, does it freeze from the bottom up or does it freeze from the top down? It freezes from the top down, right? The surface will freeze and then there will be liquid water underneath it. And because we freeze on the top, it sounds weird. It almost has like an insulating effect so that it's really hard to freeze something completely, right? Something like a lake is really difficult to freeze all the way down to the bottom because the water on top will freeze and then it'll provide an insulating effect so that the water underneath stays liquid. And this is absolutely necessary for a lot of living things. Think about the fish and the plants and other different aquatic organisms that live in that lake. If it froze all the way solid, those would probably all die. But since we just freeze over the top and the water underneath stays liquid, the fish, the plants, everything else can stay alive and they can kind of adapt to just a little bit of a chillier environment without being totally frozen. Right, and so that's what we see, right? We see that the frozen water arranges in that crystalline lattice, and you see how they're more spaced out compared to the liquid water. Liquid water, they can kind of form these close hydrogen bonds, far, like distant hydrogen bonds, but here we end up with this like crystalline structure where everyone's kind of equidistant, and that makes it less dense. Our last thing is that water is a good solvent, meaning you can dissolve a lot of different things in water. Not just solids, but also gases and other liquids. Right? That means we can use water as a form of transport. We can move things around, and on a microscopic level and a large level. We can move things around inside the cell, from one cell to another, through soil, huge bodies of water. Right? We can move stuff. It's good for transport. Salt water doesn't freeze well either because we can dissolve things like salt in it. So those ions, the sodium, the chloride ions, are going to disrupt the crystalline lattice, which also reinforces the high heat capacity and reinforces it staying a liquid. So we can dissolve a lot of things. Think about like anytime you make like Kool-Aid or you make salt water for your pasta or whatever it is you're making, right? You put some sort of solid in your water, you give it a good stir, and that solid seemingly disappears. Right? It's because water is a good solvent. Anything that's ionic, we can break down into the individual ions. So if we look at a bunch of salt, right? Take some salt, put it in a glass of water, give it a stir. This is what's happening on an atomic level. That the sodium and the chlorine have been pulled away from each other, and the reason they're able to be pulled away is because water is polar. So the slightly negative charges are going to help surround the positive sodium, and the slightly positive ends of water are going to surround the negative chloride ion.